Okay, I'm going to start. This talk is about building composable UIs. And when I say that, I mean including like the data fetching portion of it, because today there's a lot of I/O in UIs. Like there's AJAX calls, there's network requests, there's WebSockets, and type of thing. And I think immutability may provide a solution. So this quote, which most of you have read already, is from Pete Hunt, who at the time that he said it in 2014 was an engineering manager at Facebook. He was talking about what's bad about REST and why Facebook doesn't use REST. And the problem is that it does a lot of I/O. Like if you want to have a REST service, it might look something like this. So there's like you can navigate across links, like you've got your data that comes out of the database. Let me see my mouse. You've got your data out of the database right here, and you've got links to other resources. Like your data is a graph. You can't join everything in. You can't join 6 layers deep. So when you have like a sufficiently complicated UI, like you might say, well, this is like my profile, and I need to navigate like to the events, or I need to navigate to like the friends list, or I need to navigate to my photos, and you kind of traverse a graph. But the problem is, that's tons and tons of requests. Each time you navigate to like a different portion of the UI, you need to do more I/O. And that causes a lot of problems. So for example, this is like a pathological REST service that's given no regard to performance. We're just trying to make it like as abstract as possible. So this is what a collection endpoint might look like. Nothing's joined in. Like a lot of the times when we write our backend services, like by default, we're going to want, if we were want to say like select the first 10 results and then join all the records in, because it would be too slow to fetch them one at a time as needed. So this would be really slow. If I wanted to draw this in a UI, like I need to navigate each of these links individually. And that's really, really slow. So unfortunately, we end up needing to create custom backend code in all of our backend web services, like for each individual UI. And that's called the backend for front-end pattern. And I think it's more of an anti-pattern. Because the problem is, like your web-facing Facebook property like needs a certain amount of data, so you're going to join all that in and try to make that into like as fast of a request as possible. You're going to try to join in all the pieces you want and send it in one go. But that's not the same information that the iOS app needs. And that's not the same information that the Android app needs. Like they all need to have different queries, and the programmer needs to think about this, and the programmer needs to hand optimize the queries. So he's not only writing, generally SQL on the back end, like with these optimized joins, he's also trying to batch this stuff on the front end. He's trying to make the minimum number of AJAX requests, or whatever your data syncing mechanism is. It's really complicated. And it leads so you can't have a general backend. Like whatever your database state is, your API, like we wish you could just have one. You could write the business logic once and have it work for everything. But because it's far too slow, we ended up writing all these different backend services like that optimize specifically to what the front end we need. And this is an explosion of poisonous complexity. It also is complicated because what if you're running an elastic configuration? Your caches need to be synchronized. So if I have like multiple elastic instances of this web service, and my laptop user on Facebook hits one backend and makes a query that comes out of cache in this service. And then he makes another query on the same page, and he makes a query and it's a different elastic instance. Like you might have different query results. Like there's no notion of time in our caches to force the cache to be consistent. See, it's just like kind of like loosey-goosey, and that's kind of like what the flaw is with NoSQL. We've given up consistency. But if only there was a way to have consistent reads out of our caches. So that leads us to our problem statement. When we write like enterprise scale interfaces today, there's an explosion of asynchronous code. So all throughout your front end code, you're using like promises or core async or RX or all these abstractions that are just meant to like make async things easier to work with. But the problem is that it had to be async in the first place. Like why does this need to be asynchronous? Second, anything where you're doing I/O, you need to consider the performance consideration. So our entire front-end application, every single line of code in it nearly has to think about the performance cost of doing something, of fetching the data. And it's the same on the back end. We have to optimize our queries and consider like, well, if I make this query and then do code that dynamically decides to do this or this other query, like, well, that has latency. And also, any point of this I/O can fail. So we need to like have complicated error mechanism handling. So like our promises have ways to like propagate the error through our asynchronous callbacks. And like that's okay, but like what if we could make it not fail in the first place? What if we could make failure impossible? And all these things totally break functional composition. So if you want to compose functions, well, your functions can't do I/O. You know, if you want, you can use promises and try to compose them with promises, but you're still doing I/O. It's just harder. And this is all extremely hard to test. So if only we could always read from cache. So fortunately, as programmers, we are aware of a system that always reads from cache, and that system is Git. So Git is, in its essence, an immutable time series database. So when you work with Git, you clone a copy of the database onto your local machine, and then your coworker on his computer clones his own copy of the database. But there's a notion of time wired throughout your database. So you can say, well, as of this shot, I want to make this complicated query, like show me the history of this file, or whatever. And he can make the same query on his machine from his cache. And there's no need to go talk to github.com. There's no need to do any I/O. There's not really a way for it to fail, and it's not asynchronous. So a time series immutable database gives us the tool we need to do consistent reads from cache. And this is a really profound thing because it changes the way we think about writing our code. Because we no longer have to reason about doing I/O to fetch our data. And this is kind of why Git is so good, if you think about it. So let's talk about a way to represent this stuff, like our object graph, which you generally store in something like SQL. Let's think about how we can represent that as a time series. So up at the top is a simple graph that has 3 nodes. There's the node with identity 100, the name is Dustin, and the country is an ID. So that's a reference to this node in the graph, which has ID 100, label USA whatever. And here's a third node in the graph that also has a reference to the same node. So this is a graph. Like you can traverse it by doing like a foreign key lookup on the ID, for example. So this is an alternate notation for the same graph. We've basically converted it into a time series by, at each point in time, we say, well, ID 100 has the attribute named Dustin, and ID 100 also has the attribute of country 100. So if I wanted to like implement a change on this database, I could append to this list something that says ID 100 has name Dustin2 now. So the latest one always wins, which is kind of like Git. Like if I have a file with multiple changes to it, the latest commit always wins. So there's a database that does this. It's called Datomic. And as far as I know, it's one of the only ones that does. So this is an ACID database, but it can do the queries out of cache. So you no longer have to make like a round trip to the Postgres server to run a query, which is like Git. You don't have to go to github.com to run your query. You can run it locally on your machine. So when we think about graphs, sometimes when we're doing UI programming, it's useful to think about it as a tree. Like if you wanted to draw like Dustin, you might want to have like an inline UI component that shows like this sub-attribute of it. But notice that this guy got duplicated. So if I wanted to make a change to this, like the UI needs to make sure that that also changed this. So like you've denormalized it in order to represent it as a tree. So trees is generally how people encode their application state in front end today. But really it's a graph. It's a graph in the database. So we're kind of using the wrong abstraction. So if we have a time series database, what if ignoring performance and security considerations, we could just clone the whole database? I mean, I'll get to that. But what if we could clone the whole database to the browser? Like, what would that mean? Well, for starters, it means we can run queries without caring about the latency cost of them, because it's not I/O. It's all pure code, pure functions against local data. Which means you don't have an enormous asynchronous, failure-prone I/O thing threaded throughout your entire application. Your front end, it could be a pure expression if only you had all the data locally. So it really solves all our problems if only we could do it performantly and securely, because you can't put like a gigabyte of data or a terabyte of data or whatever into your browser. So this is a slide borrowed with permission from a blog called The Web After Tomorrow, which is excellent. You should read this. The slide is from Nikita Prokopov. And it demonstrates an immutable time series architecture that solves, ideally, our performance and security concerns. Because this is like our immutable time series database. Now you can filter this time series to get like the data that a user is allowed to look at. And then further, you can filter it again by saying, well, if I have advanced knowledge of what the UI data is going to need, I can make sure that only the data that they need is sent to the browser. So if we could somehow implement these two filters of our time series, we don't have a performance or security problem. We can actually have exactly the data we need in our browser. We can code our apps as pure functions and make them composable in that fashion. We no longer, so for example, we no longer care about making hundreds of requests, as I showed, like through that simple REST API, where you gotta keep clicking links to navigate through it, like they're not requests, it's all local data. So if we could do this, what might our code look like? So I'm not sure if this audience can read Clojure, but this is a pure function. So like you can see, like you're returning, a div here, and inside of that div, we're saying, hey, I'm declaring a data dependency on the results of this query. So if the data was somehow made to be inlined, well, we can just use our regular functional combinators to operate on those, like the map abstraction. You can just map over the list and continue to resolve the pieces we need. And the pieces we don't need will never be resolved. So this code needs to be written like in a portable language that can be run on both the browser and in the server layer. So if I'm running the code in the browser, well, the data is already local and fast. But I can also run that same piece of code in this like middle layer JVM piece that can somehow like inspect the code and run it and see what the data dependencies are going to be, so it can like compute, which 4 pieces is the UI going to need to render this page. So by running this piece of code in multiple places, making it portable across the browser and the backend, we can solve our performance and security problem. So there's other front-end systems, like if we just take React.js, they advertise UI as a function of state. So like in React, you have a render function and it returns DOM as a value, and its input to that function is like the state of your application. But really that's kind of a lie, because the UI is more than just state to HTML, it's also data fetching. So when people say UI is a function of state, like that's misleading. Really your front end is a function of state and data sync. So you need to solve this problem. So here's an example of what might be possible if we could do this. So this code is copy-pasted from like the real prototype I've made. So there's no lies in this. Like this is actually the real code. And this is the result of that code. So like what the arguments, like we have this like CJ form, this is just a function. And it takes like an object in the graph, that's what this is, by ID, rel means ID. And it takes like the template, which is like a self-describing way of, it says like it's the metadata needed to render this form. And in doing that, okay, so it can take the data and it can take the metadata and it can render this form. But since it's a graph, we can like traverse further into it. So I'm going to try to show this here. So this is a fully general hypermedia client. So what that means is it takes this hypermedia API, which like I can navigate around kind of like the web. And each piece of this API contains both the data, it also contains a thing called template, which is the metadata. So like this describes, like this is the metadata, this is how to render the form. Like we've got like the type information of the string, it's got like the combo box options for it, and it's got a link to the query powering the combo box options. Some of these things are a reference type, which means like you can navigate it further. This is set notation in Clojure, so this is actually a set of references, and I can keep navigating further. So from this hypermedia API, we can have a fully general hypermedia client, which, so here's a collection view, and notice like it's resolved all of the references in this collection. So it's made, like you could think like conceptually, it made like 100 requests to draw this UI. But since the data was inline, it actually did it in 0 requests. It was really fast. So here's a form, a metadata-driven form for it. Since it's a graph, we can like recurse deeper into the graph. And we don't care about the performance impact of doing this. So I can say, oh, well, actually, I need to create a new, whatever thing this is in my model. And I can do this, all at the top level. So like I've got like full control of attaching my form to a graph. What else can we do? Also, since the form is a graph, you could imagine like traversing a path through the graph that has cycles on it. So I don't have a demo of that, unfortunately, here. But that would mean like as I type into this, I could theoretically have like this could be the same reference in the graph as this. And as I type here, the UI should update it here also. So you can implement reactive queries even in this fashion. And this, conceptually, the programming model, The programming model is just a pure function against local data. It's really fast. Recursive graph traversal. You can go there on your phone if you want to play around with it. It even server-side renders because the UI is just a function, so it doesn't matter where you run that function. You can run that function on the server, you can run it on the client. You can cache the output of that function at all layers because everything's immutable. You can store it in a CDN, you can store the database in a CDN, you can do all sorts of caching to make the system really fast. So in conclusion, this is just kind of research, like this isn't a thing you can use yet. We hope maybe it will be soon. But we really think that this sort of addresses like the failure of like hypermedia REST APIs that used to be popular in like the 2000s and they just sort of died. It's because they're too slow and they're too failure prone. But this we think fixes it. That's my content. Any questions?
So do you use DataMake at the back end, or?
I'm sorry?
Do you use DataMake at the back end, or what data?
Yeah, this is implemented on top of Datomic, but really essentially you just need any time series database. Like you could build it on Git, for example. Or some sort of event source thing.
Have you played with Meteor's like publish subscribe system at all? It's like this reminds me a lot of it, except like much more advanced in your case here. Have you played with that at all? I was just curious.
I played with it a little bit. The problem is
Okay.
that I don't, to my knowledge, it's not immutable, so it doesn't have an
Okay.
of time. So
Okay.
you can build systems like this on top of things that give up the ACID guarantees.
Okay.
But that's not acceptable
Okay.
to some applications.
Do you work for Cognitect?
I don't.
Just kind of sounded like it.
How close is this idea to event source systems?
It's very close. You
Okay.
could, so this is just sort of like what would a UI look like if you built it on top of an event
Okay,
source
so I have a
system.
follow-up question.
Right.
So in event source systems, you have a situation, scenario when those events grow and grow after like 10 years, you have a huge database of those events, and going through the whole journal of events is really time consuming. They came up with ideas like serialization of that stuff. So is it something you do research for, or is
Well,
it
the
already?
UI only needs to see a little piece of it. Like it only needs to know the pieces needed to draw the UI. So you're really only looking at the recent stuff for most UIs.
Well, it only needs that amount of data as the user needs, right?
That's right.
So, but if you have scenarios where that data is actually, big.
Well, kind of the theory behind Datomic is that storage is growing faster than we can consume it. So don't worry about it. That's my understanding.
If Datomic uses some kind of, like, say, Git hashes or something, I guess, to identify the triples in time or something like that, or?
Datomic just uses like a monotonically increasing integer, more or less, which is like the same. You just need enrichment time.
So you use backend JVM-based code to figure out what data to return, to filter. Have you considered pushing that to the client and having the client simply ask the backend for the data it wants, like Falcor or Relay, in that style, like the way Facebook solved that with Falcor, right?
That actually we do that. It works. It's just not as fast.
No, that's nice.
Yes, I guess. Like you could do it either way. You could fetch it.
Have you looked into content-based hashing on something decentralized like IPFS?
Not really. I know what IPFS is. I'm not sure.
Yeah, I saw a talk where they were trying to host a REST API on IPFS. It seems like it might be an alignment.
It probably is. Like this is just like a research prototype, but it's like we could decouple from Datomic and back it. Like if IPFS provides immutable namespace or whatever, we will store. Sure.
What do you do when you don't know in advance what data the user is going to want to look at?
So when I say that the code is a pure function, like this is a composable programming model, but like I've shown the guts to be honest. Like there's a callback here. So this resolve function will resolve synchronously. It'll call the callback immediately when the data is local, and that darn well better be the case in 99% of the time. But if for some reason the data couldn't be predicted in inline, then it will make a request, and this go run asynchronously. But that is bad. Like ideally, you want something in the back end that like tries to predict what the data will be based on like algorithms or something.
I mean, so you've got like a database of metadata about a city. What if our database is actually all cities in the world, and we don't know which cities the user is going to be interested in? What are we going to do when they search for a city that we didn't predict them to be interested in?
So it's kind of like, how does the cache warm up the first time? Well, it'll run asynchronously the first time if it needs to, and it'll be slow. Like you could even think of it like it needs to be a loading screen the very first time, potentially, if it couldn't be inline.
So what you were talking about with Datomic sounds kind of like, I happen to be using event source, which uses the concept of streams. And one of the things that it does is it exposes its events as an atom feed, effectively, where each of the events is a link off of that atom feed, and then it throws on cache headers on there that says this event is immutable, you can cache it forever.
Sure.
Which allows you to do something like push that down towards the client and
Sure.
have them just be reaching at their local cache for those types of things.
It sounds very similar. Yeah.
Yeah, event store, yes.
Yeah, you could absolutely build this UI system on top of it.
Maybe you covered this, but I'm not clear what you do in the case where there are changes and you need to invalidate this stuff cached on the browser and download new data.
Well, the cache is never invalidated, it's only appended to.
All right.
So like in Git, like you need to push a new commit to the browser. So the server-
Same difference. So
Sure.
how is that communicated?
Well, the deltas are very small, so you get, say, a WebSocket between the client and the server. So as like Datomic has like a transaction stream that it just sprays to all people connected to it, and you can filter that transaction stream and send the relevant pieces to the client in a push, because Git is pull, but like it could be done as a push.
Okay.
Or you could just wait till they refresh the page. I mean, that's what we do today anyway. Like how real time does it need to be? But this can support real time by pushing.
So extending the Git analogy, if I want to commit something and someone else has already committed something, we need to either rebase or merge. Is there an equivalent in this system?
One thing you can see in this thing is, like, where does the state of the form as I type into it go? So that's what this local datums thing is. So in the browser, there's like a pseudo transaction, which is not published to the server yet as you type into the form. So that's why, like, when you're rendering, like, it's really querying the graph, and we're adding to the graph as we type into it, but the transaction hasn't been pushed. So like when I go to say, hey server, I want to commit this set of transactions that I have locally, which can be arbitrarily nested. It can be any data tree transaction, anything you could think of. The server can reject it. Someone beat you, that's invalid. You could run your own validation logic.
I guess I was working on something similar, and I was thinking when you have a page open, it can subscribe to the list of updates for that model, and then I was kind of picturing like when someone else pushes changes to something that you're looking at, I could like hide the one you're in the middle of editing as red or something, or I don't know, like apply diffs.
Sure, absolutely, yeah. So if we had a WebSocket hooked up where transactions were being streamed to the browser, and it like was a merge conflict against like my local thing, yeah, you should flag it red. We could implement that. Because it's going to fail when you go to commit it.
To that point as well, one of the problems with Get's merge is that it doesn't have semantic information about the text files that it's actually trying to merge. So when it hits a merge conflict, it doesn't know necessarily how to resolve it. Whereas here you have a data structure where you have semantic information where you could perform a smarter merge. So you might not hit that as frequently as you do.
Yeah, I agree. And you can run code to inspect the transaction and determine if it's going to fail or not. If it's ought to fail or not. Thank you.